Hello, everyone. My name is Yue Lin. I'm from Forest Systems in Scion. Today, I'm going to present some of our work on next generation growth and yield simulators. Thank you. The title is, today I'm going to present next generation growth and yield simulators. In New Zealand, currently, the models and simulators used for forest growth and yield have been normally classified as stand growth models. Those kind of stand models and simulators are not spatially explicit, means not individual tree have been identified in those models. And those model and simulators quite often cannot provide sufficient resolution of the yield predictions to solve many of the problems that facing forest managers. So there's a call for next generation forest growth simulators. We believe that the new simulators must represent the state of the art in forest growth simulators. And it also should address the requirements of forest growers and stakeholders. By doing this, we held 2 workshops and collecting the feedbacks and the needs from all our stakeholders and the forest growers. There are here is a list for the top 5 needs arised. First one, they ask not only just the growth functions. It means that in the model, the growth should of the trees should also include the mortality, size distribution, taper, and the tree competitions as well. This represents the mechanistic model rather than a statistic model. Also in the simulator, people require distance-dependent individual tree-based models. That means the trees must have their location and should be spatially explicit. Also, in the simulator, people should have silviculture and management planning tools that they can use for their management. This simulator also need to be flexible framework that can add in extensions and functions such like carbon and wood properties for their future use. Also, the simulator should be able to handle dealing with big data, not only from PSP data that we currently have, but also from the modern technology collected data, such like the LiDAR data that can be also used for modeling purpose. So according to all their requirements, we comes to this idea, a new forest growth simulator, which called PyReady. Currently, this is still an alpha version, but we have developed a prototype showing the functionality of the simulator. As we can see, this simulator can meet the basic requirements from the stakeholders. It is not only the statistic growth function, but beyond that, we have a mechanistic growth functions. All trees, as we can see, have their exactly locations in the simulator have been presented. And you can use this also for your silviculture and management purpose. This model is very flexible that you can extend to other purpose and develop further model procedures and submodels and use on different platforms. This model is also be able to use multiple big data entry interface. So what's the special about this model? The most important thing is that our model is not a purely statistic model as the old simulators used. It is based on mechanistic model, which we use metabolic scaling theory and dynamic energy budget theory. So all those physical and physiological processes have been considered in our model and represented. And our model also able to include the biomass allocation in the model, so you can consider different purpose use of the model for your real daily management. Our model also includes and represent the mortality of trees that can be due to local tree-tree interaction competition. And our model is also flexible, that you can also use your empirical growth functions for modeling purpose. So we really include not only the traditional statistic model, but also the mechanistic model. Also, our model is able to simulate the tree-tree interactions. By doing this, we developed this zone of influence approach. As you can see, each of the zone of influence of the tree represents the space, physical space, or the resource that tree can occupy. And the tree competition happens when their zone of influence overlapped. They compete for the limited resource that in the overlapped area, which represent different mechanism of resource competition that include the above ground competition for light and the below ground competition for the nutrient and water. And by doing this, we are also able to include different competition that happens among interspecific trees or intraspecific trees. Also, our model also represents the key processes that of tree environmental interactions, that environmental constraints on tree growth have also been included in our model, such like resource level and abiotic stress. That gives you the simulation of different tree growth when they grow in different environment conditions, which is also important when you consider site differences. And also in our model, we can also include spatial explicit tree locations. So each individual tree's location have been recorded and represented in the simulator. You can develop your own spatial deployment for your management purpose, such like to study different initial spatial pattern and the effects on tree growth and the size inequality. You also can use this to develop different management scenarios, such like different thinning strategies and also selective harvesting approaches. And by using this spatially exploit trees, you are also able to develop uneven aged stands, such like mixed genotypes or species that can simulate more complicated structures of your stand, which cannot be done in formal models and simulators. Our model is also able to handling really big data, such like you can control the model settings and develop your own scenarios by using a user interface, but you can also import manually the sample plot data that used in a formal database, such like PSP. And the special thing in our model is that our model can also import LiDAR data directly. So by using this approach, you can identify individual trees that have been detected and recorded in the forest. And you can also import this LiDAR tree cloud into the model and identify each individual tree and identify tree metrics that you use to derive measures of microsite and competition, such like competition experience by each of the tree. As you can see here in the figure, that middle one was identified by the LiDAR, arrow LiDAR, and the right model interface is imported data. From this, you can also start your simulation and make prediction on the future standard dynamics at individual tree level. Also, currently, our simulator already developed a graphic user interface, but we also make it, because it's based on really free platforms and very flexible. We also develop different interface that can be used from different platforms, such like this model is currently built on NetLogo, which is a JavaScript language. And people or end users can access the model from the web browser or their mobile devices easily. And we also develop an R extension that can be used by the advanced users. They can use R to control the model, call the model, make their own settings, develop their own scenarios, and to run the model to collect the data for their further analysis. At the same time, our model is also able to communicate and connect to R that can call R functions for the analysis in the model at the same time. We are also developing a Python extension. Currently, it's under development. So for in the future, Python users can also use our model from Python and can communicate. Our model can also communicate with Python labs. So there's definitely more works that need to improve our model. So we already displayed and present this model to some of our stakeholders and the users and collect their feedbacks. We think that in the next 12 months, there are 3 key processes we would like to do for our model simulator improvement. First is the further development and improvement, especially the parameterization and the collaboration, so people can use the model for their real work and test the model. And also we are going to include more environmental factors, such like soil and topography. And also climate inputs will be also built into the simulator. So people can also use the model for making future predictions on their yield on the background of global warming scenario. And also we are going to improve the silviculture and management functions, such like fertilizing, pruning, and thinning, make all those management tools more easier use for managers. In the next 2 or 3 years, we are going to extend the model current function and the sub-models. We are going to include the wood properties, weed management, pests and disease, and also for fire functions into the model. And we are going to develop a connection between the simulator and existing model systems, such like YTGene and Forecaster, so people can also flexibly use this model and with the tools that they're familiar with. Also, we are going to develop more precise 3D visualization and more detailed tree architectures in our model. And user interface and visual recommender will also be developed for the easier use of the model. Thank you for your attention.